Welcome to this tutorial. Today we want to do introduction to real analysis. So if you are faster being introduced to real analysis, this is what you need to note. So these are the basis for real analysis. Real analysis is a pure mathematics unit and is very important in mathematics. So welcome. If you have not subscribed to this channel, kindly subscribe so that every time I post a tutorial, you are the first one to get notified. Share with your friends also so that they subscribe to this channel. So welcome. Real number. First introduction to real analysis. We start with real number system. Real number system. This is the Vic Academy. So this is a foundation of real analysis, as I have just quoted. Real numbers have the following subdivisions. Remember, we have two types of numbers. We have real numbers and imaginary numbers, which sometimes we call them complex numbers. So in this case, we are generally discussing real numbers. So they have the following subdivisions. We have first set of natural numbers, which we have a double capital N, which are lies on this set. 1, 2, 3, those are equivalent to what we call whole numbers. They are natural numbers. Then we have integers, and we note it in double Z, capital Z, which are the both positive and negatives of natural numbers. So you can see that. Then we have rational numbers, which we denote with the double Q, capital Q, which is actually equivalent to what we call fractions, P over. So we have denominator here and we have the numerator. So where P and Q are members of integers. But in this case, the denominator, which is Q, should not be equal to 0, because if that happens, then this becomes undefined. We have irrational numbers, which are now the complement part of rational number. So you'll see that we can't express them in this format, that form. So like root 2 pi, exponents, sin pi, and etc. Okay, so let's start with the first thing. First, in subdivision, those are the properties of natural numbers. Two set, we divide this as two sets that a set that denoted by this in which natural number n as a successor n plus 1, then we say that n has the following properties. And these properties are actually called peano axioms. We call them peano axioms. So if you have a given set and we have a given small n with a successor being n plus 1, and if you have those two conditions, the peano axioms will have to follow. Number 1, identity will be in the group or in the set n will still be in that natural set, and again n plus 1 again is in that set. And remember, 1, which is the identity, cannot be a successor of n. So it's always a predecessor. 1 is always a predecessor. So those are called peano axioms. 1 is a member of n, small n is a member of capital N, and a successor n plus 1 is still in n. And the key to note is that 1 cannot be a successor of an element of n. So if m and n you have two elements, M and N, being members of that national set, and they have same successor, then that will imply that M and N are same. They are same. M and N are same. Again, if we let S to be in an element of a set of N, in N, set of natural numbers, and we know that identity is in S, and its predecessor is also in S, N plus 1 is in S. Whenever N is in S, then automatically to imply that this S again is a natural set. It's a natural set because it has the peano component. It has 1, it has N, and N plus 1 being in it, and 1 is not succeeding, it's not success of 8 of N, and therefore it is a success. It's a national, N becomes a natural set. So what you need to note here is that the 80th axiom from the basis of mathematical induction asserts that certain propositions, which may be first proposition P1 and P2 second proposition, and that they are true provided that they will be true provided that the first assertion is true. The first assertion or the proposition, we call them basis of the induction. We call them basis of induction. Then it implies that the next N plus 1 insertion is also true, and whenever the first one, the Pn, is true. So if you find P1 is true and Pn is true, then it implies that Pn plus 1 is also true, and that's called induction state. So this is one way of proving in pure mathematics, which we call mathematical induction, and we'll meet a lot of proofs that we'll be doing using mathematical induction. Okay, we can look at an example whereby we are going to apply mathematical induction to come up with the solution. So for example, prove by induction that 7 power n minus 4 power n is a multiple of 3 for all n being a member of the natural set. So we are talking about natural set. So because we are talking about natural set, we are talking about whole numbers here, 1, 2, 3, like that. Okay, so if we want to use induction method here, we have to test whether n being equal to 1 is true, and if we do that, we'll find this is giving us 3, and the 3 is actually a multiple of 3, isn't it? So therefore P1 is true. Next assertion should be, we look at Pn, whether Pn is true. So simply we assume Pn is true. And that is 7n minus that is actually a multiple of 3. And a multiple of 3 is surely a multiple of 3. Yeah. So now this is a multiple of assuming that that's a multiple of 3, since lambda is also a member of the natural set. So now we'll look at n plus 1. So n plus 1, that one. So what you need to do is to expand that so that it befits our interest. So you see, if you break it in that way, so it reduces a 7 here and a 4n here. Okay, let's factorize. So factoring out, we get that and that. But what's this? That is basically this. Okay, so substituting back, we have that, and this gives us 3, meaning if we factor out, we'll have 3 outside there, and we have this. But you know lambda is a member of the natural set. That implies that whichever is the bracket here is still also a member of the natural set, and that will mean that this is also truly a multiple of 3. And then by doing so, we have proven that this particular equation here is a multiple of 3. It's a multiple of 3. So if you have question on this, kindly leave a comment and we'll be able to look at it. Until next time.